All right, welcome. Today, we are going on a bit of a journey. We're going to dive deep into, well, the blueprint of reality itself. I'm talking about the real number line and all of the amazing spaces that we can build from it. Okay, think about this for a second. What's the simplest thing you can possibly draw? A line, right? It just seems solid, continuous, no breaks. But is it really? I mean, how can we be absolutely sure there aren't these tiny, microscopic, invisible holes just hiding out between the numbers? Well, to find out for sure, we've got to go straight to the source. And for us, that's Chapter 1 of Gerald Marston's Elementary Classical Analysis. You can think of this book as kind of like the official rulebook for how numbers in space actually work. So let's start with something we all know, right? The good old number line. We can plot our whole numbers, we can plot our fractions, but here's the big question. Are those numbers enough? Do they create a truly complete solid line? And here's the problem. It turns out if you only use fractions, what mathematicians call the rational numbers, you actually leave these tiny invisible gaps all over the place. Think about a number like the square root of 2. We know it has a place on the line, but you can't write it as a fraction. So with a fractions-only line, it just falls through the cracks. And this isn't just some minor detail, this matters a lot. Because if you're trying to do something like calculus, which is all about describing smooth, continuous change, you just can't have a universe full of mathematical potholes. It wouldn't work. So to fix this, to build a truly solid, gap-free line, mathematicians had to lay down the law. They created a set of rules, or axioms. Honestly, the best way to think about them is like a constitution for numbers. Every single number that wants a spot on that line has to play by these rules. And these rules come in 3 main flavors. First, you've got your basic arithmetic rules, the field axioms. These just say you can add, subtract, multiply, and divide. You know, the stuff you'd expect. Then you have the ordering rules, or order axioms. These let you tell if one number is bigger or smaller than another. But the real star of the show, the one we're really interested in, is the third one, the no gaps rule, the completeness axiom. This is the special rule that plugs all those holes. All right, so let's get to the main event, that completeness axiom. This is the big one. This is the rule that separates the kind of holy Swiss cheese-like line of rational numbers from the solid, real numbers that we need for, well, everything. Calculus, physics, engineering, basically any field that tries to describe the world around us. Now, the definition sounds a bit academic, I know, but the idea behind it is actually pretty simple. Imagine you have a collection of numbers, and you know that every single one of them is less than, say, 5. So your set has numbers in it like 2, 3.5, 4.9, 4.9999, and it keeps getting closer and closer. What the completeness axiom does is it guarantees that there is a smallest possible ceiling for that set, a least upper bound. And in our case, what is that number? It's exactly 5. The axiom promises that the number 5 is there, waiting to be the perfect boundary. And this diagram shows it perfectly. You see that set of numbers S? Now, there are lots of numbers bigger than everything in S. But the completeness axiom promises that this one special point exists, the least upper bound. It's like the perfect cap that seals off the set, leaving absolutely no room for a gap or a hole right where the boundary should be. It's the mathematical guarantee of a solid line. Okay, so we did it. We've built a perfect, one-dimensional, gap-free line. But why stop there? Now, let's take this perfect building block and see what kind of universe we can build with it. Yeah, what happens when we go beyond just a simple line? What if we use this perfect ruler of ours to start measuring things like area or volume, or maybe even dimensions that we can't even see? And here it is. Welcome to Euclidean n space, or Rn. What you're seeing here is that beautiful progression. We start with R1, that's our solid number line. Then we get R2, a flat two-dimensional plane, like a piece of paper. Then R3, the three-dimensional space that we all live and breathe in. And the cool part is, it doesn't stop there. We can go to Rn, a space with any number of dimensions you can imagine. So how does this actually work? It's simpler than it sounds. Rn is really just a way of describing a point using a list of n numbers. So a point in 2D space, R2, just needs 2 numbers, an x, y. A point in 3D space, R3, needs 3, x, y, z. And here's the absolute key. Every single one of those numbers in the coordinates is a real number, pulled from that complete, gap-free line we just built. It's that solid foundation that makes these bigger, higher dimensional spaces just as solid and continuous as the line itself. Okay, so we're now in this huge multi-dimensional space. We're going to need a toolkit to navigate, right? How do you even measure things like distance or length or direction when you're not just on a simple line anymore? Well, it turns out we have three essential tools for the job. First up, vectors. The easiest way to think of a vector is as an arrow that gives you a direction and a distance. It's like saying, go 2 blocks east and 3 blocks north. It tells you where to go and how far. Next, we have the norm. It sounds fancy, but it's really just the mathematical word for the length of that vector. And finally, we have the inner product. This is a really cool way of multiplying two vectors together that tells you something about the angle between them. And what's so great is that these tools aren't just abstract formulas. They have real, intuitive, geometric meanings. You can see here on the left how that inner product helps us figure out lengths and angles. And on the right, you see the famous triangle inequality. This idea, which we all know intuitively, that the shortest path between 2 points is a straight line. It comes directly from the math of these tools. It's amazing how it formalizes something we just feel is true. So, at the end of the day, why does any of this matter? Well, let's hear it straight from the author, Gerald Marsden. He puts it perfectly. He says that without this rock-solid understanding of the real line and these n-spaces, the entire structure of advanced calculus, the math that describes literally everything from how planets move to how water flows, it would all just fall apart. It's that fundamental. This foundation, it's everything. This isn't just abstract math for the sake of it. This is the stage. It's the very stage on which we build our models of the entire universe. So we've built the stage. It's solid, it's complete, it's ready. The question now is, what kind of action can happen on it? What amazing phenomena, both mathematical and physical, are we now equipped to explore in this perfectly defined space?